And it's May 16th. Oh, I gotta turn my board on. Okay. The simplest thing is a circuit is just a closed path for current. Closed path for current to flow. And there are only three things that a circuit needs to be a circuit. It needs a source. Oops, I spell source right next time. Source. Now, specifically, that means a source of voltage. So you need something to make voltage. Whatever that happens to be, you can do a lot of different things to make voltage, but it don't have a circuit unless there's voltage. You just have a coil of wire. Speaking of that, you need a wire or somewhere for that voltage to go. Some kind of conductor. So, some kind of place for those charges to move. And then, a load. Or resistor. Something for that energy to do. Some place for that work to go. So, when you have a source of the voltage, you need somewhere for that voltage to go. You need that voltage to do something. It can't do nothing. That's not how energy works. Energy has to do something. And so that's what we're doing. It has to work, so it has to do work. Now, I'm going to show you all the fancy symbols that we're going to use, because we're going to do a lot of this in diagram. I saw some of you flip over to the next page. They all look like that. So good news is that I only get to draw a few of them for this page, and every other one I print using a computer, so it's easier to read and you don't have to look at my diagrams. The first thing we're going to draw here is a battery, which is a series of long and short lines connected to wires on each side. So when we have a battery like this, the long side is the plus side of the battery and the short side is the negative side of the battery. And then we're going to connect this to a few other pieces. So going from the top, we're going to move it over. I'm going to draw a dot here with a line and then another dot right below that line. This piece of the circuit is a switch that makes the circuit connect, turn on, or off. Now, we won't use a lot of switches in our problem solving because it's not a before and after much. Mostly, it's a continuous snapshot. And then we get to draw a few other things that we're going to put into this circuit. The first thing is the symbol for resistor, which is this zigzaggy line. So this is a resistor. In other words, something that's using the electricity. Resistor. So a resistor symbol is that zigzaggy line on a page. It can be a light bulb, it can be a heater, it can be a motor, it can be anything that can use electricity. So anything that can use electricity, that is the resistor. It's a placeholder for that. It tells us how much electricity it's being used. And I'm going to include the light bulb symbol. It has its own symbol. It looks like this. And it has a circle around it. There. Let me finish writing this. This is the light bulb symbol. It is a resistor. So these are the same things. I didn't write it in here, but this is battery. So it's included in the notes. That's a battery, or specifically our source. So those are basically the symbols. Most of what we're going to do is just a patterns of resistors. And resistors are just things that do work. Now, what most resistors that we do, and especially in the lab that we're going to try with this, is most resistors just get hot. They just do heat work. That's most of what they do as controlling the system. It's why when you look at electronics, they have like those vents in them because electronic components get warm when they're turned on. So a lot of things just make heat. All right, a few other symbols that you need to know what they are. They are very boring. This is what we know as an ammeter. And it has the symbol A with a line in a circle. It's very boring. this is the measuring device for a current, right? Ammeters measure how much current there is. So if I want to know there's 2 amps of current in the circuit, I have an ammeter in the circuit, and it's just a symbol for what that is. The other one is, very excitingly, called a voltmeter. And that measures the voltage on each side of a resistor. I drew them differently, and the reasons for those will become apparent later, but now that they're written in that way, you'll notice. Basically, ammeters are in line of a circuit, and voltmeters are put around a circuit, like on each side of what they're measuring. That's basically the difference. Okay, there are only 2 types of circuits, and then combinations of those 2 types of circuits. This is just the 2 types. One is really boring, which is the series, which is 1 path. There's 1 path for a series circuit. So I'm going to draw it like this, draw a battery, and you will see very quickly my personal preference with these batteries is I almost always draw the battery up on the left of the page. They're just a circle, so it doesn't actually matter where. But I'm going to connect it to a resistor here, and then I'm going to connect it to another resistor here, and then one final resistor on the bottom. And I'm going to creatively call these resistor 1 with a subscript, resistor 2 with a subscript, and resistor 3. Very creative names, but hopefully we can see where they all come from. And at the battery is where we measure totals. So at the full circuit, we're measuring at the battery, and so this is a voltage total. But I can also measure the resistance of the total circuit is the resistance at the battery, or the current at the battery is the total. That's where we measure totals from. Totals are at the battery. The parallel circuit is slightly harder to draw, but I'm going to start it in the same way. I'm going to draw my long lines and short lines. There's my battery, and I'm going to draw multiple paths. So I'm going to draw 1 loop with a resistor in it, and connect it back, and then another loop with a resistor in it, and connect it back, and one other loop, because I want both of these pictures to have 3 resistors in them. They don't need 3, they can have 2 or more, but I just want them to match. So parallel circuits have multiple paths. So there's more than one way for all of the source current at the battery to make it back to the other side of the battery. Because what do the charges want to do? They want to get out of the positive side and back to the negative side. That's where the charge wants to go. And so in this case, there are multiple ways for that charge to find its way back. In this case, if I leave here, I have to go through all 3 before I can come back. So it's 1 path for charge to go. So charge can go in the first path, or the second path, or the third path, or if I'm in the first circuit, I have to go through all resistors one by one. I don't have any opportunities to avoid them. I'm going to throw in the labels here. We're just going to call this one back to R1, R2, and R3. So we're just labeling them, and it's still my total voltage here, there. All right. So these are the 2 different kinds of circuits. These are things you may have seen in 9th grade, the 2 different types of circuits. Do they look familiar a little bit? None at all? A little, like just familiar with it? Okay, so what you probably didn't do is the different rules for measuring voltage, current, and resistance in both of those circuits. And the most annoying thing is that the rules are different for both. The straight up rules are different, and so which circuit you're in tells you how to do the different rules. This is the main chunk of it. These rules are on your formula sheet, so that you don't need to memorize the rules per se, but you do need to be very familiar with these rules, and so you can solve the problems you need to solve. So I'm going to slide down, and so I'm going to write out, these are called Kirchhoff's laws. I like how it's supposed to K and a CH both given the K sound, but that's what happens when we let other countries speak different languages, and everyone speaks different, so we start pronouncing things different. It's awful. Okay, current is the first one. Current so I'm under each of these things. So the first column is all the first column is all the series rules, and the second column is all the parallel rules. First rule is all the current in a series circuit is all the same. So all the currents are the same. And the little numbers below are at each of those places. So when I say the current 1, I mean the current right here through the resistor 1. That's how they balance. So if I look at the current at 2, I'm looking at the current in this part of the circuit. Now in a series circuit, when there's only one path, all the current has to be the same. There's nowhere else for the current to go. So in this one loop, all the current is going to be the same. Now, annoyingly, because I laid it out that way, that means the Kirchhoff's law for parallel is completely different. Okay, so the exact opposite is true for parallel. In this case, the total voltage is equal to all the currents added together. So I have to take the current that's in this area plus the current that's in this area plus the current that's in this area, and they all add to the current in this area. So basically all the current that's starting with the battery gets split amongst the different resistors in a parallel circuit. So these 3 resistors share the amount of current that's coming out of this part. That's the main goal there. So here's where it gets worse. The voltage in a series circuit adds up. So the total voltage is equal to the voltage at 1 plus the voltage at 2 and the voltage at 3. So how much voltage is used up in each spot, they add up. So the voltage here plus the voltage here plus the voltage here equals the total amount of voltage over here. That's the rules there. You're going to see where the annoying part is here. The voltage in 1 equals the voltage in 2, which is equal to the voltage in 3. The rules for current and voltage in each circuits are flipped. So in this case, all the voltages here equals all the voltages here equals all the voltages here. I can see the smiles already. You can see that, like, that's going to be weird. It makes sense when you think, can you get a picture around what voltage is? Voltage is the amount of push you're going to get, and so the push is coming from the source, and it's coming around, and it's getting back. So in one loop, all your voltage is consistent. Okay, the resistance rules for a series circuit are they add up. So the total resistance of the whole circuit in one path is added up. R1 plus R2 plus R3. They add up for the total. All the resistance of the circuit is equal to all the resistances added up. So if I have 10 ohms and 20 ohms and 30 ohms, I just add them up and I get a 60 ohms and I got the total of it. It's very easy. Now, the worst rule ever is the resistance rules for a parallel circuit. I have to really be careful with how I'm saying this too. Okay, so let's set this up. We're going to do 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. So when we're solving these lovely things, it's fraction math, and you can do fraction math. I'll show you guys a nice quick calculator way to do fraction math, because in this case, we're adding fractions, and what do we need for adding fractions? Common denominators for adding fractions. But that's to do it like by hand. Calculators could just add fractions just because they're just numbers. So I'll show you how to do it nicely in your calculator to make the math part of this easy. But you do need to understand how this works. But you don't have to do the like algebra by hand. That's where that goes. All right, now the whole meat of this is like, that was just what the rules are. The goal of this thing is how do we solve all the problems? Now these ones are, the first step is to tell me what type it is. What type of circuit of the two? It's a series circuit. It's a one loop series circuit. So first step, this is series. So it's only series. There's no parallel in it. So we can use only the rules for series. So only the first rules apply to this particular circuit. And they're labeled 1 and 2. And they're different. So that's okay. Resistor 1 is a 4 ohm resistor. Resistor 2 is 3 ohms. And I know my battery is currently supplying 14 volts to this thing. Now I want to point out some of the labeling we're going to do. This is the voltage total in this case. So this is what like saying. So at the battery is where all the totals go. So anything labeled with T in those kinds of things, you have to see, that's at the battery. So total is at the battery. All right. So we want to find the voltage and current and resistance of every resistor in the diagram. So basically, we want to find the three things about electricity we learned yesterday at every point on the circuit. That's the main goal. So it's kind of like solving the trigonometric triangles where you find each side and each angle. Those kinds of things. You just find everything. Okay, so we can go in a lot of different directions here, but I think the easiest one to do is find the total resistance first. So first step is total resistance. Resistance total. Now we're going to show you like the long way where all these numbers come from, and then I'm going to show you a shortcut way because each of the math steps is very easy. The only trouble comes from which ones to do. Each math step is extremely easy. So what is the rules for resistance total in a series circuit? Yeah, we're just going to add the two. So I'm going to show you this with R1 plus R2. So it's just 4.0 ohms plus 3.0 ohms equals 7.0 ohms. So I know my total resistance of this particular circuit is 7. That's it. 7. First step done. So I also want to find out what the total amount of current is. I think that's next. Total current. What's the rule for total current? Well, all the current's the same. So if I find one current, I have found all the currents. Now this is where I have to bring back yesterday's lesson. Do I know any of the currents so far? No, I know none of the currents. None of them are labeled in the diagram. So the only way to do that is using my voltage and my resistance using Ohm's law. So I still have to remember Ohm's law, V is equal to IR. That's the other thing we're using. We're using the rules that we got on the first page plus Ohm's law, and that's it for like theory stuff. Everything else is just mush the two together. So how do I rearrange Ohm's law for current? Yeah, so it's V over R. Yeah, I got it right. So VT over RT, this way. So that's the way that one gets done, and they're all going to match. So you got to see that like this, if this is the total current, then it's the total voltage and the total resistance. We want to match all those labels. So if I want the current at 1, I have to do the voltage at 1 and the resistance at 1. I want to match all of those things up. So now that we know all these things, back to the pen, voltage total is 14, and we have the resistance total is 7. So, as I said, the math steps are easy. A lot of the time you will not need your calculator because they're very nice, easy fractions, multiplications, and so on. So, we have 2 amps at the total. But that also means that that's the same as I1 and the same as I2. So all the current everywhere in this loop is 2 because in one loop all the current is the same. All right. So now we got to do what's the things we don't know now? We don't know voltages at each of the resistors. So I got to find out how much voltage is going through here and how much voltage is going through here. The answer is they're both not 14, right? What's the rule for voltage in a loop? They add, right? So the amount of voltage here plus the amount of voltage here equals the total. So I know that this number plus this number equals 14, but I don't know that. And so 7 and 7 will work if the resistors are the same. So if those two resistors are both the same, you can cut it in half and that totally works. Our resistors are not the same, so that rule won't work. So what we're going to do is we're going to do Ohm's law for each one. But that is a very important skill. If you notice they're both the same, you can cut it in half and be done with the problem. Though that is a true statement if the resistors are the same. So it's a good question. So we're going to do the voltage at 1 is equal to the current at 1 times the resistance at 1. So we're going to look at each one individually. So the voltage at 1 is equal to the current at 1 times the resistance at 1. It's a heck of a mouthful, but it's a simple multiplication. So the current is 2 everywhere. It's always 2. And the resistance at the first one is 4. And so this is just 8. So I know it's 8 volts at the first one. The first one has 8 volts going through it. Now we can do the second one in 2 different ways. I'm just going to follow it because I think it's the most simple. Is V2 is just I2 and R2 together, which is 2 amps of current and 3 ohms of resistance. So that's going to give me 6. And this allows me to be consistent. What do I know about the 2 voltages? They have to add to the total. So does 8 plus 6 equal 14? Yes, it does. So when you're done these particular circuits, they are all self-consistent. So once you find all the things, they all work with all the other things. All the currents work, all the resistances work, all of them add up or are the same consistently. So when you're finished, you know you're finished because they all work together. So you can do this last one. I'm just going to say this once here, is that if I found the first one is 8, I can go 14 minus 8 is 6, and that's totally fine to find the second voltage. It's a perfectly good strategy. As I said in the intro, there are many, many correct strategies. To start this one, what kind of circuit is it? It's a full parallel. So it's a parallel, so we're going to use the parallel. There's no series in it, so it's just the parallel rules. We have to do a couple of labels here. This is my total voltage here, right? Where is this ammeter pointing to? So we're looking at this. We're just trying to figure out what this one is doing. Is it the total current, the current at 1, or the current at 2? It's one of those 3 things. This is going to be the current at the battery, so total. So this is my pen back on. This is IT. Now, how we can determine that is because it's connected to the battery. It's in one line with the battery. So anywhere before this point, before this split, anywhere in here would be the total. Anywhere in this line, because they're just connected by a wire. So there's no splits, there's nothing, no resistors in the middle, nothing's in the middle. So this is actually the total. So it's right beside the battery. It's in that chunk of the circuit. So that one's a little bit, now I had to be clear with that. Okay, so I have been given the total voltage and one of the resistances, so I don't even know the other resistor. And I can find all 3 things about all 3 places. So we're going to use, first is the voltage rule. What's the voltage rule for parallel? They're all the same. So before we go, I'm just going to write right on top of the screen. This time I'm not going to show my math because it's not really math to show. I know that the voltage equals 12 volts. I know that's true. It's 12 volts there. And I know this one has 12 volts here. We can do that math. They all have to have 12 volts because it's a parallel circuit. So V1, I guess I'm going to write that there, and that's V2, I guess. I didn't write that very clearly, but it's each of those resistors has 12 volts. The volts come out of here, and it goes full 12 through there, full 12 through there. You get all the voltage through these things. This allows me to do my totals here and here because I have 2 out of the 3 pieces for Ohm's law. Ohm's law has 3 pieces: voltage, current, resistance. If you have any 2 of them, you can find the third just by doing your multiplication or division. So the first one we're going to do is the total. I think it's easy. So let's do the total resistance. So the total resistance can be done in a parallel circuit with that ugly fraction math, but we're not going to do that because we can do this with Ohm's law, and we can say the resistance total is the voltage total divided by the current total, right? That's the shorter way to do this in a parallel circuit. And I know voltage total and I know current total. This is going to be 12 divided by 5. Very exciting. Now this one, you probably want to get your calculator out. You probably can't simplify that off the top of your head. Some of you can, but don't be afraid to use your calculators. It is 2.4 ohms of resistance. So the total amount of resistance in this particular circuit is 2.4 ohms. And you might look at that and go, that can't be right. What makes you think that can't be right?
Because of R1.
Yeah, R1 is 3. So how is the total resistance less than one of the other resistors? And that's because of parallel. Because if you look at the rules for parallels, they add up as fractions. And so that's how you're allowed to have that number being smaller. It will always be smaller. It's kind of weird that way. It's how fractions work. You can try the math on them later. Okay, so next one we want to do, we have all the things we need here. We have 2 out of 3 here, so we're going to find this one. So let's find the current here. So we're going to try to look for the current at 1, which is going to be the voltage at 1 divided by the resistance at 1. So we're going to use Ohm's law for 1 in the next case. Anytime we have 2 out of 3 of Ohm's law, we should solve for the third one because it'll make other things better. Voltage 1 is still 12, and the resistance at 1 is 3. Good. I didn't need my calculator for this one. We get 4 amps. So we get 4 amps at 1. So here I can just write in, sometimes it's useful to write in 4 amps there. Sometimes it's useful to write all the 3 things besides where they are. So if I write here, I've got 5 amps here and 2.4 ohms here. These are all the things that are total at the battery. Sometimes that's a very useful way of laying out the problem. So those are true. So I only have one thing over here. I got to get both the current and the resistance over here. I only have the voltage. That's all I know. How can I can get both of them, but there's a better one to do first. I can do the fraction adding to get the resistance over here. Who wants to do a subtraction of fractions? No one. No one wants to do the subtraction of factors. Sometimes it will come that you have to, but it's usually can work around it. So I'm going to try to find the current here first. What is going to be the current here at 2? That would be the better choice. What's the rules for current in a parallel circuit? They add up. So the current at 2 is equal to the total current minus the first current. So I can do a subtraction to find what is missing. I know all of the current is 5 amps, and I know the first one has 4 amps. So I'm left with 1 amp of current at the end. So I know at the very end of this little thing here, I'm going to get 1 amp of current over here. Now I have voltage and current. I can solve for the resistance using Ohm's law. Now I will use Ohm's law. Resistance at 2 is equal to the voltage at 2 divided by the current at 2. I know the voltage is 12, and I know the current is 1. Good, no calculator again. There's 12 ohms of resistance at that point. So now I have all three measurements at all three locations. That's the way we do all these. So for me, this is one pattern that we can show. We're going to say, I have to find the voltage, I have to find the current, and I have to find the resistor at three places. So what I'm going to do is I'm going to make a table of all my answers. So we're going to find everything at 1, and I got to find everything at 2, and I got to find everything total. So really what I'm doing here is I'm making a table of responses. So that's my goal here. It doesn't need to be the prettiest table, but it does have to be readable. So this is the way I like to solve these circuits. Only has 2 resistors in it, and they can get more and more resistors in them, but it always lays out. So the first thing I want to write in, and I'm going to write them in my red pen, all the things that we know out of the gate. We didn't have to do any math on them, things that are just given in the picture. So I'm going to look at the first number. Where should this part go? The 6 volts. What is that labeling?
The total.
That's my total voltage, so that's going to go here. I'm going to write 6.0 volts right there. The other thing I know, what is the 0.4 measuring up at the top there?
The total I.
No. Right here, where should the 0.4 go? It's an amps, right? It's given in amps, so it is an I, it's a current. So it should go at 1, right? It's just the current here. But what else do I know about that current? It's the same all the way down. So we know it's here. So I'm going to write it here, and I'm going to leave it there for now because that's all that's given. So that's technically me using a rule. Oops, not 4 point. Yeah, backwards. It's 0.4, 0.4. And what's the other number at the bottom? It's a resistance at 2. So I'm going to write 3.0 here. So I'm going to leave this just as it is in this color because this shows me what's given in the question. And the rest, I have to use rules to fill it out. So you did correctly point out, and we've said it already, that the current in this single loop is always the same. So I know that this is going to be 0.4, this is going to be 0.4. They're all going to be 0.4. That's really easy. And now I'm going to look across the labels here. I'm going to look like in this line and in this line. If I ever have 2 out of 3, I can do an Ohm's law fraction. So I'm just going to write here beside it the rules I did. I did I1 equals I2 equals I total. They're all equal. So that was the first rule I did. I'm going to do the voltage in 2 next. The voltage in 2 is I2 times R2. We just multiply those two together. So 0.4 times 3 should be 1.2. Because 4 times 3 is 12. We know how to do that. And then we can do the total one next. So the next one I was going to do is the resistance total, which is voltage total over current total. Got to remember my Ohm's law. Okay, so that's the next one I'm going to do. That one gets me 6 and 4, so it's voltage. 6 divided by 0.4 is... 6 divided by 0.4 is 15. So I get 15 ohms there. Well, you can just try the calculator out. 6 divided by 0.4 is 15, yes. It's kind of weird, but it's true. Just trust your calculators. If it's not an easy fraction, just use your calculator. It's fine. Okay, So now I'm looking at the top one and I see like no pattern here. Like I just have one out of it. So I've got to use Kirchhoff's rules, which go up and down. So which one should I do first? Both are reasonably easy, right? There's not really a better way which one to do first. Both are just going to be subtractions because they're both following the add up rule. Voltages add up and resistances add up. So let's do the voltages first. They're on the left. So how much voltage needs to be at 1? Yeah, I think that's right. Voltage total minus voltage at 2. And that's the math I did. So it is 4.8. We can subtract. And then we can do the resistance at 1, which will be, oops, that's the wrong color, but that's fine. Resistance total minus resistance 2. There, I got that right. So 15 minus 3 is 12. Now I have, because my table is full, I know I finished this question. I've got all the things done. I have my table full. And they're always in the table consistent. So I can do the multiplication across here, I can do the multiplication across here, and I can do the multiplication across here. If they're all true, everything is correct. So 0.4 times 12 is 4.8. That's true. It's not the way we did it, but it's still true, and so therefore it's still correct. I can go 0.4, I did that one already, so 0.4 times 15 is 6. Those are true. So we can do those all the way through. Are they consistent? Then it's all correct. This one's challenging because it's both. This is both, oops, pen on, both series and parallel. So this is both, so it's a bit tricky. But we're still going to do the same setup. So at the top of this page, I'm going to write out my columns. So I have a voltage column, I have a current column, and I have a resistance column. And I know I have one resistor, two resistors, three resistors, and a total. So I've got 4 columns that I need to deal with here. So those are going to be fine. It's not a pretty picture in this case because I'm going probably a little too fast. And we're going to start with all the things that we know are just given in the question. So given in the question, we can start laying out, I know that the total current is 8 because that's here. I know resistor 1, although all the resistors are 3. So that's 3 there, 3 there, and 3 there. So each of the 3 resistors is there, and that's it. That's all the things we've been given so far, right? That's kind of crazy. None of the layers have 2 out of 3, so we can't do any Ohm's law stuff. The only thing that we have most of, we can do just one. So I'm going to see if I can go the other way around this. One of the ways we can do this is I know one other current. Which other current do I know? I only know one of the other currents. I know the series current. So if I'm looking here at the battery here, is there any splits between these? No splits is a series, no current change. So the current here and the current here are the same. They have to be the same because there's no splits. There's nowhere for the current to go. It has to go from here to here. The current is the same. So I know the first new thing I have to do is that's 8 ohms. They're the same. 8 amps. They're the same. There's no difference there. And I also see a super convenient thing about the bottom 2. What do I know about the bottom 2 resistors?
They're the same.
They're the same. So what do I know about their currents?
The currents are also going to be
They have to be the same. Now, do they get 8 or do they get 4? Because that's the point. Like, I'm going to see that, like, the current's here, it's coming down here, and then it splits here. I get a little bit there and a little bit there. So each of those currents are half because they're the same. So we get to do a little bit of sneaky math here. This is the same as that, so I know that they've split it evenly. We know they share it, but we know they share it evenly because they're the same. So we can put both of those at 4. Isn't that awesome? It's really handy, isn't it? So now we got a lot of 2's, right? We can do the Ohm's law for all of them, right? And the Ohm's law for all of them is just multiply because I have current and resistance. So times, times, times. I'm going a little fast to this part, but hopefully it'll make sense going fast. So we can times each of these. Times, times, times. Let's do each of those multiplications. Those are going to be 24, 12, and 12. Nice, easy maths for those ones. Great. Okay, can we get the total voltage? Now, when we do total voltage, I'm going to just write this as a sentence because it's super common as a mistake. Total voltage is in one loop with the battery. So if you pick one loop with the battery, that's the total voltage. So the total voltage in this case is not 48, right? It's not add all of them up. It's in one full loop. So if we take one loop to be this loop, the top loop, or the bottom loop. So either way, we skip one of the bottom 2 resistors. So the total voltage in this case is 36, 12 plus 24. It's this voltage plus this voltage back to the battery. I get this one plus this one back to the battery. Or I get this one and this one back to the battery. Both ways is 36, not just add this all up. You have to always apply this to this picture. So finishing this up, this is 36 in this case. It's not let me keep it there, back in the right spot. So total voltage in one loop with a battery is the total voltage. So that tells me that's 36. Now I got through this whole thing without having to use fractions, didn't I? Because I could have done the fraction math to add up this column. Gross, right? Didn't want to do that. But I can do a simple division here. The resistance here is just going to be voltage total over current total. So that's going to be 36 over 8. It's 4.5. So now I'm going to get all the way down to 4.5, and that's all the way done. I have finished it. I did it. I got it all done.